All right, let's go ahead and look at some of the information necessary to work on the module folder 3C pre-lab for calorimetry. Okay, so once again, this one has a simulation, so we've got a link that goes to that, and we have basically one initial instructions that we want to go to the experiment tab. Now, you do need to be careful with this. Unfortunately, there are a lot of little things, there are a lot of options that we can work through. I think it's a decent trade-off though, because otherwise this would be a very expensive piece of equipment, and this gives us access to simulation where we can use that equipment if we otherwise aren't going to have it. Okay, so let's read through and see what we've got going on. Like I said, unfortunately, we are going to have kind of a lot of instructions for these. So, all right, let's get to it. We're going to use a solid. We're going to set our solid to be iron. Okay, and then we want to show specific heat. And eventually we'll tweak some other stuff, but for now, according to this, the specific heat is 0.449. That's joules per gram degree Celsius. So there are several options that there could be. Sometimes it's kilojoules and kilograms, sometimes it's calories. There are a few different options here. For this particular lab, we're using joules per gram degree Celsius. Okay, so that's that one. Okay, most of this is going to be the same, right? So if you've done the step and you didn't reset anything or touch anything else, then we should be able to pick up partway through and move on. Okay, so we want to set the mass at 50 grams. So that looks like the maximum mass we can set that block. That was kind of a nice touch in the animation. You can see the size change there. Okay, so 50 grams. We want the temperature to be 100. So that's right about the middle. And then we're going to hit next. So that means we're going to be done messing with this. We've got a sample of, pretty hot iron there. Then now we're going to set some information about the liquid. Well, our liquid, we're going to use water. So starting from here. So liquid, choose a liquid, water. Then show specific heat, kind of like we did for the other one. This one's still here, so 4.184. That number technically does change between temperature and pressure and some other stuff. Excuse me. So, we do want to be careful to look at the value that's here. And for other assignments, you want to look at whatever value is given to you, because technically that's not always consistent between different sources. Okay, so if we look, that's this one, 4.184. Okay, and I know the next part looks like a whole ton of instructions, but we get to skip pretty far down if we've already got some progress going. Okay, so with our water, we want to set to 50 grams of water, which I believe is the minimum. We are not allowed to change the temperature. That's picked for us. Okay, and then we want to hit next and eventually run the setup. So now we have some final settings. Might as well go ahead and just turn everything on. Be careful not to hit reset here, or else you'll have to go back to the beginning. But then we'll click start. So what we're going to see is that the block gets teleported over here. Notice the water level increases. This is meant to show you the molecules bump into each other and share energy. And then this graph here shows us how the temperature changes over time. So notice that the black line for water, it's not technically straight, but it's fairly straight overall, very reasonably well approximated by a straight-ish line. Whereas the lighter color, this is gray, has a really deep, steep drop at the beginning and then levels out. Eventually, they're going to be done sharing energy and they're going to reach some temperature together. So from the digital readout, that's 27.75. All right, so that's what we're looking for here, 27.75. Okay, so a lot of this is the same as what we did before. Again, reading the instructions here skips to step 14 unless you accidentally reset. So if you reset early, you'd have to rerun that whole first part. So hopefully you didn't. We want to look at that final temperature and some of our earlier settings, and we want to figure out what was the change in temperature of the iron. Okay, so we can look back from here. The iron was 100. And then we're not looking here at the water, but we're looking at the readout to see what it got down to. We know it's somewhere between 120 because this was our starting temperature for each thing, but this readout is going to tell us, basically how far between. Okay, so we'd have 100 minus 27.75. So pretty big change in temperature for that metal, over 70 degrees Celsius, which is, that's quite a bit. Okay, then similar work. Again, lots and lots of instructions, but if you don't reset anything until you're told to, then this part should be easy. Find the change in temperature of the water. Either look at the settings from here or look at the settings from here. The water started at 20, right? And then only got up to 27.75. Not a very big change overall. Essentially just sort of cover up that 2, and it's the rest of it, isn't it? So 7.75. How do the changes in temperatures for the different substances compare to each other, right? So the metal changed temperature by over 70 degrees, and the water changed temperature by like a little less than 8. So it seems like there's a very big difference, right? So the change in temperature of the metal was a lot more than the change in temperature of the water. That seems correct. No change in temperature for either one. That's definitely wrong. Change in temperature of the water was a lot more. That's definitely wrong. Change in temperature is the same. No. All right. So for me, it was that first one. For anybody, I would hope that would be obvious. If nothing else, look at the big curve, right? So giant change for the light gray line, minimal change for the dark black line. Here's the tricky part, though. We want to see if we can guess why that might have happened. Okay, and with this one, 2 of the choices are technically correct, like true things that happened. Only one of them is actually the cause of this, so do be a little bit careful here. The specific heat of the metal is a lot lower than the specific heat of the water. That is true. All right, let's go through our choices. Let's find the 2 true ones and see what's going on. Everything was the same. Well, definitely not true. We had 50 grams of each, so the mass was the same, but the temperatures are different, the substances were different, so yeah, B is wrong. The metal was a lot hotter than the water before the experiment. Okay, that's the other thing that's true. A lot of times students will look at D, or the one that's D for me here. There was more mass of water than mass of metal, and they start thinking about mass, and sometimes they mix in density and like size, volume. But that's not true here. Both of these were 50 grams, so it has nothing to do with mass here. We're looking between A and C. And like I said, both of those things are technically true. But if we look at C, it says the metal was a lot hotter than the water. Yes. However, if that was important, that the metal was hot, then I feel like that would have made the graph, the opposite, a reflection of what it showed. So if the metal being very hot mattered as much, then we would have seen the water level come up a lot more, and it just didn't. So what happens, specific heat, we finally kind of get to the meat of this, is lower for metal. That means basically that it's easier for the metal to change temperature. We want to think of specific heat as being like resistance to a change in temperature. And so if it's lower, there's less resistance and it's easier for the temperature to change. Well, that seems to be what we saw. It's easier for the metal temperature to change, so it changes by a greater factor. Yeah, I mean that seems to show it. Okay, then a few more. This time we do want to reset, and we're going to make a few other little small changes for different scenarios just to sort of read out and see how they play. Give us something that we can potentially talk about later. Okay, so yes, finally, for real, on purpose, reset. So notice everything went away. To get started, we're going to do a lot of the same stuff, but this time we're going to make the iron really hot. So this is our way of sort of checking our question 7. is that if we make the metal a lot hotter, like even hotter, is it going to have more control over the outcome? All right, so solids, iron, mass, still 50, yes, but temperature, 200. Show the specific heat because why not at this point? Then water is going to be the same. We're going to have 50 grams of water. It doesn't allow us to change the temperature, and then we're going to run it and see what happens. So liquid, water, mass is 50, which is the minimum. Show specific heat because why not? Turn on the graphs because again, why not? Start it, let it run. Okay, so look at that. That gray line just absolutely dives at the beginning. The black line, again, almost looks like a straight line for part of this, and then it sort of curves and goes flat. Okay, so even steeper gray line, less steep black line. What's the question? Record the final temperature. Okay, so right here, right in the middle at the top, 37.44 degrees Celsius. If you think about it, that was the only choice that would have made sense here, right? If the metal is hotter, it is going to bring the temperature up some more. It's not going to bring it to 100 and something degrees like that. That's way too much. That C is the same as before. My letter B, 7.75 is less. That was the temperature difference from before. So yeah, 37.44 is what we're looking at. All right, we're going to reset again. But this time, we're going to have iron at 100 degrees, and then a whole bunch of water, right? Mass at 200 grams. So we're setting the iron back basically to what it was before. So maximum here, 100 degrees, which was about the middle. Water, it was 200, right? Yeah, 200 grams. We're not allowed to change the temperature, so that's 20. Show the specific heat because we can. Okay, so notice we have a lot more water, same temperatures as we had in the initial run of this. Let's show the graphs and let it go. That gray line's almost a straight line down here at that beginning part, and this black line is almost horizontal the whole time. So the water has a higher specific heat, about 9 times as big as what the iron is. But now we even have just a lot more of it. So first of all, water is harder to heat up in the beginning, and now we have even more of it, and so it's going to have even less of an impact. So, very minimal change for the water, enormous change for the metal. Okay, so 22.09, that's this one. The only two that would have even really made sense would have been 22.09 and 24.44. It wouldn't have been the same as it was before, and it's not going to be all the way down to 20. The water's going to have to change at least a little bit. So there we go. And then last one, a little bit different here, and you might have a little bit of a guess. If you think about it, you might be able to figure it out. But we're going to have 100 grams of water and 100 grams of water. So same stuff, same mass, but 100 degrees Celsius on this one and 0 degrees Celsius on the other one. So maybe you can think about what that might be. But let's go ahead and reset and rebuild and see what we get. So water, we're going to set to 100. Okay, and again, 100 is on both of these, the mass and the temperature. Okay, that's the maximum. Think about it. Why would that be the maximum? What happens at 100 degrees Celsius? What would happen if I push that to go hotter? Okay, this liquid is also going to be water. 100 grams to balance and get the same thing. Temperature is 0. Kind of a similar thing here, but on the other end. Why do you think the minimum temperature might be 0? How come we can't go any lower? What would happen below 0 degrees Celsius? All right, turn the specific heat on because we can, just to further indicate that these are the same material, same specific heat. Then turn on our fancy graphs and let her go. All right, so water mixes with water. And now notice that bottom line is actually coming up this time and coming up pretty quickly. sort of a looks like a reflection here, right? So now they balance out, they meet somewhere in the middle. In this case, the actual middle, the average between these two. So the fact that there was the same mass, the same specific heat, basically everything was fair, then neither one of these samples is going to take full control. They're just going to essentially share temperature and then meet exactly in the middle. The average between 0 and 100 is 50. If you think about it, if there had been more hot water, then it would have been a higher temperature. If there had been more cold water, it would have been a lower temperature. But the fact, again, that everything was fair, equal, shared, then we met at the average temperature. So 50 degrees. All right, and that should be it.